Okay, so the last thing we're going to talk about, and you're not going to do a lot of problems on it, and just between you and me, I'm not going to put any questions on the test on this, but I just want to get this in your notes and whatever, have you see it. So we're going to talk about the refrigeration cycle today. Oh, before I do that, let's talk about what we still have coming up. So this is the last new material. We have quiz 3 today. And then for our 2 classes next week, I'm just going to do some review. Well, one of those is a test, right? So I guess on Tuesday, I'm going to do a little review of the recent stuff, and we'll see, maybe we'll have time to work on some problems, but it'll all just be sort of prep for the end of the semester. And then next Thursday, we have 2 of these classes, right? So Thursday is our exam 3. I'm going to put a quiz 4 in with it. Let's see, how do I want to do this? Exam 3 and quiz 4 is next Thursday. So that's what, the 8th? I think that's what the syllabus said. Do you remember, either of you? Let me just make sure. Oh, this is the one that's, the syllabus is wrong. Okay, so we're going to do exam 3, quiz 4 on Thursday the 8th. And then the last thing is just exam 4. And that is Thursday, 12/8, 11:30 to 2:30 in room P 2842. $15. Yeah. So let me just check those times and stuff. Okay, 2842. Yes, that is right. And you guys have a weekly assignment that's out right now, right? Okay, so this is it. That's the end of the semester. And everything after today is just trying to get ready for that stuff. I don't think I'm going to. I was thinking about it, but I think I'm just going to do that. Just those. There's 4, right?
Yeah.
You're working on your 4th?
Yeah.
Yeah, let's just go with 4. Make the soft call. Okay. So The last thing we're going to talk about is the refrigeration cycle. And we are going to talk about a Carnot refrigeration cycle briefly. And an ideal, what we'll call the ideal refrigeration cycle. The Carnot refrigeration cycle looks like this. Since a refrigeration cycle is an engine in reverse, the states go in the reverse order. So 1, 2, 3, 4, like that. And the ideal refrigeration cycle, and I'll talk about why we have to make the changes from the Carnot cycle to this. So there's state 1, state 2, state 3, state 4. So these are going around counterclockwise. Okay, so I'm going to start with the Carnot cycle. And it looks like this. You have a compressor going from state 1 to state 2. And this is isentropic. Then you have a condenser going from state 2 to state 3. And that condenser is isobaric, just like it was for the Rankine power cycle. And then you have an isentropic turbine going from state 3 to state 4. And then you have an evaporator going from state 4 to state 1. And this is isobaric. Marshall! We missed you on Tuesday. We were just talking about how much we missed you.
Good. Thank you. Oh, it sucked to miss class on Tuesday. I had to correct my sleep schedule from Thanksgiving weekend.
Oh, yeah. Okay, so this is what's going on, and let's talk about it for a second. So the more than you hear the term Carnot refrigeration cycle, you hear of Carnot engines. And this is all fully reversible. The evaporator and the condenser are both taking place with no temperature difference. That's not a realistic thing, but that's the way it's modeled. And so you can fully run these in reverse. And so if you go 4, 3, 2, 1, you can see that this is an engine where that turbine provides work, and the compressor requires work. And let's, I guess, talk about what goes where with this. Work has to be done for the compressor, so I'm going to call that W dot sub C. Heat. So for any condenser, heat is leaving the working fluid and into the environment. So I'm going to call this Q sub C. Those two C's mean different things, but one's a Q and one's a W, so you can keep it straight. The turbine is providing work. And then the evaporator, heat is coming from a reservoir to the working fluid. So this is the heat, Q. And actually, you know what, let's relabel these. Let's call this the heat coming in. And let's just call this the heat going out instead of Q sub C. And so if you run this thing in reverse, you get work out at the turbine, then it condenses, goes through a compressor, picks up heat here at what would be the boiler, and then goes through the turbine again. So you could run this in reverse, and that's a Carnot engine. In our case, we're doing it in order 1, 2, 3, 4, and it's providing refrigeration. So how does it work? I mentioned this just in passing once before, but all refrigeration cycles are based on this one sort of idea. And the idea is that this Q in is coming from the reservoir. Let's call this the cold reservoir. And so the trick is, how do you get heat to come in from the cold place and go out at the hot place? That's the goal of a refrigeration cycle. This one up here is warm. That's just the surroundings. And the trick to doing it is this compressor. You know that if you compress something adiabatically, you compress a gas adiabatically, there's no heat transfer. As you compress it, the temperature and pressure go up. And so if your working fluid goes into this compressor, the temperature goes up. You compress it enough that the temperature is higher than the surroundings. Then you can get energy to be rejected through heat to the surroundings. And you've removed energy from your working fluid. Now you go back through the rest of the system, let the temperature and pressure go down again, let it go down enough that the temperature of the working fluid is now lower than the inside of the cold reservoir that you're trying to cool down. And now heat can transfer from the cold reservoir to your working fluid. And so without adding energy to your working fluid, you can get heat transfer from the cold and drop that energy off at the hot. That's how a refrigeration cycle works. One more thing about this. Did you know your refrigerator has a turbine in it to produce work? No, because it doesn't. But this is a Carnot cycle, and so that turbine is in there. It's a Carnot engine if you go in reverse. We'll see that for practical reasons, you don't use a turbine, you just use a throttling device to change the temperature and pressure. Okay, so that will be replaced when we go to the ideal cycle. And on a temperature entropy diagram, it looks like this. There's state 1, 2, 3, 4. So this is going in this direction now. Okay, so let's talk about the steps individually. State 1 to 2 is an isentropic compression. The reason we need this is to increase the temperature and pressure, not T over P, T and P. And this requires work W sub C to go into the working fluid. Then from state 2 to 3, we have an isobaric condenser. The purpose of this is to reject heat to the surroundings. And that heat that we're rejecting is Q out, Q dot out. A condenser is always giving away heat. That's how it goes from a vapor or a mix to a liquid. And then state 3 to 4 is an isentropic turbine. This produces work W dot sub T. And it also lowers the temperature, reduces the temperature and pressure. And then the last process is 4 to 1. That's the isobaric evaporator. This takes the place of what was our boiler in a Rankine cycle. Any evaporator, in order to turn a liquid into a vapor, you need to bring heat into the working fluid. And so that's what's happening here. Heat comes in. So Q dot in from the cold reservoir or the cold region, let's call it. It's not a reservoir because you're trying to affect the temperature of that region. Okay, how do you evaluate the performance of something like this? Well, this is a fully reversible cycle, so this is a maximum efficiency refrigeration cycle. And so the maximum performance would be defined as the heat that you bring into the system. That's what you're trying to accomplish, is to get heat into the working fluid, divided by the net work done to make that happen. So this is going to be Q dot in divided by W dot at the compressor minus W dot at the turbine. That's because the turbine is doing work for you. It would be cool if it was practical to have a turbine that generated a little energy as this all happened, but we'll talk about why that's not practical. And we can rewrite this. Because if you look at the, if you do the energy balance, we have work coming in, or energy coming in the form of Q dot in plus the work done by the compressor. And that has to balance the energy going out, which takes the form of Q dot out plus the work received from the turbine. And so now if we rearrange it, we can get the W dot C minus W dot T. That's the denominator in our expression for the maximum performance, is equal to Q dot out minus Q dot in. And so you can rewrite the performance, the maximum performance, just in terms of heats, and you get Q in dot divided by Q out dot minus Q in dot. Okay, so these are the maximum performance values. Do you remember when we did our short little thing about power and refrigeration and heat pump cycles earlier, how you calculated the maximum performance of a refrigeration cycle? So we first did it in terms of heats like this, and then we said that for a reversible cycle, the ratios of those heats had to be the ratios of the temperatures. And so this came out to be the temperature of the cold reservoir divided by the temperature of the cold minus temperature of the hot. Temperature of the hot minus temperature of the cold. Well, we can show that again now, in a way that makes more sense, because, okay, so how did we go from this to that this maximum beta is equal to the temperature at the cold region divided by the temperature at the hot region minus temperature at the cold region? That was, from long ago we had that expression. Well, for a reversible cycle, or this doesn't even have to be a cycle, it's for any reversible process. We know that d big S dt is equal to Q dot over T, over temperature, plus M dot at the inlet times the specific entropy at the inlet minus M dot at the exit times the specific entropy at the exit. If it wasn't reversible, we'd also have to add on a production term, an entropy production term. But for reversible, we know that we're not producing any entropy, so that goes away. We're assuming steady state, so this goes away. And you come up with an expression that says, well, we can rearrange this as Q over M, and these are dotted, is equal to temperature times specific entropy at the exit, and I guess I'll put this in parentheses, minus specific entropy at the inlet. So that relationship has to hold for any reversible process. So now let's think about what this says at the since we're trying to figure out what's going on, you know, all that we have in this heat expression for the maximum performance is what's happening where heat is coming in. That's at the evaporator. And where heat is going out, that's at the condenser. Okay, so I'm going to use this expression to evaluate relationships at the condenser and the evaporator. Are you with me on that? All I'm trying to figure out how to get from this beta max in terms of heats to this beta max in terms of temperatures. We have this expression that has to hold for reversible processes that involves heats and temperatures. I'm going to evaluate that at all the places that are of interest to us, and then we'll see what falls out of it. And what better fall out of it is this, or I'm done. I'm leaving. Okay, so at the evaporator, so the evaporator heat is coming into the working fluid, right? That's what an evaporator has to do. You're going from a liquid to a vapor. And so that Q, the Q in has the same sign as this Q. And the evaporator is between states 4 and 1. Okay. So this says at the evaporator that Q in dot over M dot is equal to the temperature at which region is the evaporator, the hot or the cold? Cold. It's counterintuitive, but that's what it is exactly. And so this is the temperature of the cold region times the quantity specific entropy at state 1 minus specific entropy at state 4. And now let's do the same thing at the condenser. Is the heat going into the working fluid or out of the working fluid at the condenser? Out. And so the sign of Q out is opposite what it would be from this entropy equation, right? So we have negative Q dot out over M dot is equal to the temperature of, so is it the hot or the cold region at the condenser? Hot, yep. And the inlet of the condenser is state 2, and the exit is state 3. So this is S3 minus S2. And then if I change the signs, you get Q dot over M dot out is equal to TH times the quantity S2 minus S3. And so now let's rewrite our expression for beta max with the Q's in it in terms of what it's all equal to. So we have Q in divided by Q out minus Q in. So I'm going to write this as Q in dot, might as well divide everything by M dot since that's how the form we have it in. Okay, now we can do the substitutions of what we just figured out. So we have in the numerator TC times the quantity S1 minus S4. And in the denominator, we have Q out, which is TH times the quantity S2 minus S3, minus Q in, which is TC times the quantity S1 minus S4. You can see we're almost there. We have the temperatures in the right places. We almost get a cancellation of the differences in the specific entropies, but not quite. But what do you think the last step is? So what we want to end up doing is getting that quantity S1 minus S4 as a coefficient to all of those temperatures. Any idea where that's going to happen?
Wait, so S1 minus S4 has to be equal to S2 minus S3?
Yeah, that's right. And that's the case if you look at the temperature entropy diagram, you can see because of the two isentropic processes, 3 is equal to 4, 1 is equal to 2. So this is S1, this is S4, because those are isentropic processes. And so the maximum performance is the temperature at the cold reservoir divided by the temperature at the hot minus temperature at the cold. That's cool, right? Laura, right? Okay. Good. Me too.
Wait, so for a normal refrigeration cycle, wasn't it 1 minus TC over TH, was it?
Well, this is equal to 1 minus TC over TH. I mean, that's just a ratio that you can come up with.
Well, I mean, that's the same as the original refrigeration cycle?
Yeah, so for a real refrigeration cycle, the performance is 1 minus the quantity QC over QH.
Okay.
We have this thing where right, this is ideal so far. That other expression is for an actual one. Also, we're going to see that for a real refrigeration cycle, we're going to get rid of that turbine And so then it'll come out to look the way we've seen it before. But we already have this expression that says the maximum performance is the way we saw it before.
Wait, so is there, you said there, well, I guess I should just let you finish instead of talking about the turbine. But,
No, talk about it.
or the turbine, so you said there isn't a turbine, or is there a turbine and the work just goes back into the system?
The idea of the Carnot refrigeration cycle is there's a turbine and the work that it does goes back into the system.
Okay.
But in a real refrigerator, you just use something else because turbines are hard to work with and you don't get much energy out of it anyways at these differences in temperature and pressure.
Yep, yep.
So now that's everything we need to know about this Carnot refrigeration cycle. But let's think about some practical considerations. The first one is having liquid in a mixture going through the compressor is bad for compressors. You don't want liquid going through the compressor. That's called wet compression. And it damages the compressor. So if you look at the temperature entropy diagram, you can see that what we're probably going to want to do there is get state 1 all the way out here to where it's a saturated vapor. And then when you go through the compressor, you're turning it into a superheated vapor. Okay, so you don't have to deal with any liquid. And second, the turbine doesn't do much work. At this difference in enthalpies that we have in a refrigerator. It's expensive to maintain and operate. And so we're just going to replace that with a throttling device. And what a throttling device does is change the temperature and pressure without changing the enthalpy. So H4 is now equal to H3. And these two considerations give us the ideal refrigeration cycle, the one that we're going to be analyzing. It's not a Carnot cycle anymore. And it looks like this. Here's the temperature entropy diagram. This is state 1, this is state 2. So now you can see that the compressor is acting on a vapor. And this is state 3, and this is state 4. So that process from 3 to 4 is going through that throttling device. You can see that this time it's not isentropic. You can see there's an increase in entropy, but the enthalpies stay the same. Any questions about all this so far? So this is what we're going to be analyzing. And in this case, you can see if you go back to our original expression for, where was it, for beta. Well, you can think of it this way, like our true performance measure is going to be the rate of heat in divided by the network that has to be done to make this happen. We're going to get rid of this term now, and it's just going to be the rate of heat in divided by the work done by the compressor, because there's no turbine anymore.
Yeah, you said the throttling device changes the enthalpy.
It doesn't change the enthalpy, but it changes the temperature and pressure.
Okay, got it.
Okay, so basically now at this point, what I've done is just trying to motivate how we end up at this ideal refrigeration cycle. But now that the process is going to be almost the same as the Rankine power cycle, we're going to go process by process and figure out what the relationships are based on the control volume first law. Okay?
Yeah, this is pretty much like the Rankine power cycle, just reverse.
Yeah, right. A couple of places it's different,
well, at least in terms of the ES diagram.
Yeah, like in the Rankine power cycle, what is state 4 here is all the way over at the saturated liquid.
Oh, yeah.
There's a few differences, but conceptually or whatever, just the overall approach is the same, yes. Okay, so now just like the Rankine power cycle, we want to find expressions for the work of the compressor, the heat out, the work of the turbine, and the heat in. No, that's a good question. What are we calling it? I think I do call it a turbine through my notes, but the T2, so let's call it T for throttle. Okay, so let's start with the isentropic compressor. The control volume first law says dE dt is equal to Q dot minus W dot plus M dot times the quantity. I'm going to get rid of everything right now except the enthalpies. So we have the enthalpy at the inlet, which is state 1, minus enthalpy at the exit, which is state 2. There's no heat transfer. It's steady state. the compressor does work on the working fluid. So this says 0 is equal to, we have to change the sign of that work. So this is W dot positive of the compressor plus M dot times the quantity H1 minus H2. Yeah, because so the first line is using the sign convention of the first law. So that's saying if work is coming, if work is being done by the working fluid, then it would be positive. Okay. But our working fluid in the compressor is having work done on it. And so WC has the opposite sign of W. Okay, so for the Rankine cycle and for this, there are always two processes where you have to switch the sign of the Q or W, and two processes where it stays the same. Yep. So W dot C over M dot is equal to H2 minus H1. And then for the condenser, this is isobaric. Start out again with the control volume equation. At the condenser, is heat going into the working fluid or leaving the working fluid? Leaving, and that's the opposite sign of what this Q is assuming. So we have 0 is equal to negative Q dot for the condenser plus M dot times the quantity H. For the condenser, this is state 2 to state 3. Q dot for the condenser over M dot is equal to H2 minus H3. Yeah. Thank you. Then for the throttle, that one's easy. We already were given that one. H4 is just equal to H3. And the last process is going through the evaporator. This is isobaric. dE dt is equal to Q dot minus W dot plus M dot times the quantity HI minus HE. There's no work done. dE dt is 0 because it's steady state. At the evaporator, heat is coming into the working fluid, so that has the same sign as this Q dot. So this is Q dot in plus M dot. For the evaporator, the inlet is state 4, the exit is state 1. And so Q dot in over M dot is equal to H1 minus H4. And now that we have expressions for all this stuff, I mean, we can calculate the same kind of things that we did for the Rankine cycle. Let's calculate the performance measure. So beta is equal to Q in dot over W for the compressor dot. And we can divide both of those by M dot to get it into the form that we've seen. So this is equal to Q in dot over M dot divided by WC dot over M dot. And now we can just go back up to the things we just calculated. And this is equal to H1 minus H4 divided by the quantity H2 minus H1.
Could you explain for the throttle was
You know, I cannot really explain that. All I know, like I couldn't derive anything related to that, but that is just a simplified form of what a throttling device does. The temperature and the pressure change, but the enthalpy stays the same. That's about as much as I can say about it. Yeah, yes, exactly. And somehow the internal energy due to the temperature reduces at the same rate that the volume times the pressure increase. I don't know why that is, but that apparently is what happens. I'm not going to give you any problems with this. So I'm not going to go through a full example problem, but I have this one, let me write it out. You can see what kind of problems could be asked. It'll look very much like the Rankine power cycle problems. And I'll lay out like how I would go through it, but I'm not going to go through the whole thing because it would take a long time. So, okay, let's say that the refrigerant we're using is refrigerant 134A. That's one that you have stuff for in your tables. That's the working fluid. Through the condenser, the temperature is 0 degrees Celsius. So this, I said through, but this should be at exit of the condenser. And then at the exit of the evaporator, the temperature is 26 degrees Celsius. At the compressor, saturated vapor enters at 0 degrees Celsius. And at the condenser, saturated liquid exits at 26 degrees Celsius. Condenser saturated liquid. Yes. No, it exits. It exits the condenser. The condenser. That should be the. I just have these switched. I'm sorry. So the evaporator is the cold one and the condenser is the hot one. So it exits the condenser. It exits the evaporator at 0 degrees Celsius. And it exits the condenser at 26 degrees Celsius. Now it all matches, right? Yeah. The mass flow rate is 0.08 kilograms per second. And we want to calculate the compressor power. What's called the refrigeration capacity. Which is Q dot in. The coefficient of performance. And then finally, the maximum possible coefficient of performance. And I would go about this the same way that I would go about, the problems for the Rankine power cycle. I'd write out states like this. This process is an isentropic from 1 to 2 is an isentropic compression. From 2 to 3 is an isobaric condenser. From 3 to 4 is the throttling device. From 4 back to 1 is an isobaric evaporator. And then I would just start to fill out what we know about the different things. At state 1, that's entering the compressor. So we know that that is a saturated vapor at 0 degrees Celsius. From that, you can look up H1 and S1. Then since this process is isentropic, S1 is equal to S2. State 2, we know, is a superheated vapor. State 3 is a saturated liquid. And it's a saturated liquid at 26 degrees. And so we can use that to look up the pressure. Now, since 2 to 3 is an isobaric process, you know, P2 is equal to P3. And go on and on like that. It's the same process that we would follow for a Rankine cycle at this point. But we're just trying to get all of the same thing, you know. You want all the enthalpies at the different states. Any questions about that? Okay. That's it. Let's do the quiz.